Hey, I'm Cody, and you know what? Today we're going to tackle a massive question. Why do data structures and algorithms, DSA, sometimes feel just impossible? Turns out there's this huge piece of the puzzle that almost everyone skips, so let's figure out what it is together.
Okay, be honest. Have you ever just stared at some code? I'm talking dynamic programming or some gnarly graph traversal, and your brain just goes blank, right? It feels like you're trying to read the secret language that everyone else just gets. Well, let me tell you, you are definitely not alone in feeling that way.
So here's the big secret. The problem isn't you. It's not that you're not smart enough. It's the approach. See, we're all told to just dive headfirst into these super complex algorithms, but that's kind of like trying to write an entire novel before you've even learned the alphabet. It just doesn't work. We've got to build our skills from the ground up.
And to really get what I'm talking about, I want you to picture something. Imagine we're building a giant pyramid. Now, you can't just stick the pointy bit at the top and expect it to magically float there, can you? Nope. You need a massive, super solid base to hold the whole thing up.
And this pyramid, well, this is our roadmap to success. Way up at the top, that's our goal, mastering data structures and algorithms. But, and this is the important part, look at what's holding it all up. The very bottom, the foundation, is solid programming fundamentals. Then, right on top of that, you've got problem solving and logic. You just can't get to the top without building those bottom layers first. No shortcuts. Because if you skip these foundations, you're not really learning. You're just memorizing solutions. And that, my friends, is like building your pyramid on quicksand. Yeah, it might look like you're making progress for a little while, but the second you get a new, unfamiliar problem in an interview, the whole thing just crumbles. And this isn't just a theory. It has some serious real-world consequences. Get this. A whopping 87% of failed coding interviews aren't because people can't write code. It's because they can't analyze their code's efficiency. They can't answer that all-important question. Okay, so is your solution actually any good? And that comes directly from having a shaky foundation.
And how about recursion? You know, that thing that makes your head spin a little. It's a fundamental concept that's the backbone for so many advanced algorithms. So, is it any surprise that it shows up in 76% of interviews at the big tech companies? For sure not. If you don't really truly get recursion first, you're just gonna have a terrible time with things like trees, graphs, and dynamic programming.
And what about those super frustrating bugs, the ones that just crash your entire program? A solid 42% of them can be traced back to simple mistakes in memory management. See, these are all just cracks in the foundation of our pyramid, and they lead to some pretty big problems.
Okay, so how do we fix this? How do we build that solid foundation? Well, we start with the very first, most critical block, understanding code efficiency. And that means getting comfortable with time and space complexity.
Now, time complexity, it isn't about pulling out a stopwatch and timing your code. Not at all. It's about asking a really simple question. If my input data, say, doubles in size, does my code's runtime also double? Or does it quadruple? Or something else entirely? It's all about how the runtime scales as the input gets bigger.
Here, think of it like this. You're at the grocery store. One cashier and 10 customers. Okay, it works, but it's pretty slow. But what happens when 100 customers suddenly show up? It's a total nightmare, right? The line goes out the door. Now imagine that same store with 10 cashiers. Things just keep moving along. Time complexity is all about designing our code to be like that 10 cashier store, efficient and ready to scale. Let's look at a classic example, a linear search. All we're doing is looking for one item in a list by checking every single element, one by one. The core logic is exactly the same whether you're using C++, Java, or Python. It's just a simple loop. So if our list has n items, what's the worst case scenario? We have to look at all n of them, right? And that direct relationship is what we call linear time. We use this fancy thing called big O notation to describe it as ON. Just look at the chart. As the input size n gets bigger, the time it takes, or the number of operations, grows right along with it. It's a straight line. This is basically our first real tool for measuring how efficient our code is. All right, so we've covered time, but a really efficient piece of code isn't just fast, it's also smart about another super important resource, memory. And just like with time, space complexity asks a similar question. How does our memory usage grow? If we double the input data, does the memory we need also double, or does it stay pretty much the same? It's all about understanding our code's memory footprint. Check out these two ways to do the same thing. On the left, we're creating a totally new list to store results, so if the input has 1,000,000 items, we're asking for enough memory to hold another 1,000,000 items. That's ON space. But look at the one on the right. We're just modifying the original list right where it is, in place. We use a tiny, constant bit of extra memory, no matter how huge the input gets. That's O1 space. The difference between those two is massive. And here's what that actually looks like in code. See, the O of n way needs you to declare a whole new data structure, a new vector, a new array list, or a new list. But the O of 1 approach, it just works on the data that's already there. You get the exact same result, but the impact on your memory is just worlds apart. Okay, pop quiz time. Let's say you're building an app for a smartwatch, something with really limited memory. Which approach are you going to choose? The one with O of n space or the one with O of 1 space? Go on, pause and think for a second. This isn't just a random question. This is the exact kind of decision real software engineers have to make every single day. And as you keep going on this learning journey, I want you to remember this golden rule. Seriously, write it down. If a concept is confusing you, draw it out. Boxes, arrows, whatever works. And if a concept is really important, highlight it. These super simple habits can make an absolutely huge difference in your understanding. Trust me.
So what's the big takeaway from all this? First, DSA is totally achievable, but you have to build the right foundation first. And that foundation starts by really mastering time and space complexity. This isn't just some other topic to learn. It's the lens you should use to look at every single line of code you write from now on.
So you've laid the first, most important block of your pyramid. Awesome. You now have a way to measure your code's efficiency. But what's next? What's the next foundational skill you need to build on top of this? Well, we're going to find that out in the next explainer. See you then.
Hey, it's Cody. So you think you know Big O, right? Well, what if I told you that's only part of the picture? Like only 1/3 of the whole story. Today, we're going to go way beyond the basics and get into how pros really talk about performance. You ready? Let's do this. All right, let's kick things off with a little brain teaser. Is an O of n algorithm, linear time, always slow? The answer, well, it's probably not what you think. And stick with me, because by the end of this, you'll get exactly why. Okay, before we dive into the new stuff, let's just do a quick refresher on the basics. This is kind of like our map of algorithm performance. These are the big landmarks you just gotta know. All right, a quick flyby. Over on the super fast side, you've got O of 1, that's your instant gratification. Then O of log n, which is wicked fast because it keeps cutting the problem in half. O of n is our good, reliable, totally fair and linear. But then, yikes, you see that cliff? That's O of n squared from nested loops. And then the absolute beast, O of 2 to the n, where things just explode. We try to stay away from that side of town. And here's what they look like out in the wild. Grabbing an item from an array by its index, boom, O of 1. A binary search on a sorted list, that's your classic O of log n. The real goal here is to get that sixth sense, to just look at a piece of code and instantly feel what its complexity is. Okay, pop quiz time. Ready? I'm showing you some code. It's a for loop inside another for loop. Both run n times. What's the big O? You got 3, 2, 1, times up. It's O of n squared, of course. You go through the outer loop once, you have to do the entire inner loop. That's the textbook quadratic pattern right there. Hope you got it. Okay, landmarks are down. Now let's learn the language to talk about them. And we've got to start with a rock star everyone knows, right? Big O. But what is it actually telling us? Think of Big O as your most pessimistic friend, the one who always brings an umbrella. It's the absolute upper bound on performance. It's a guarantee that says, hey, look, on your absolute worst day with the worst possible data, it will never get any slower than this. It's your worst case safety net. Let's make this real with a linear search. So you're looking for something in an unsorted list. What's the absolute worst thing that could happen? Well, the item isn't even there. So you have to go through every single item, all n of them. And that, my friends, is exactly why we say its worst case is O of n. All right, if Big O is the pessimist, meet its super optimistic twin, Big Omega. If Big O is the performance ceiling, then Omega is the floor. It's all about the best case scenario. So Big Omega is all about this question. What if everything goes perfectly? What if I get the luckiest input imaginable? It tells you the absolute fastest an algorithm can ever be. It's a guarantee that says you're not going to beat the speed. This is the best it gets. Okay, back to our linear search. What's the lottery winning scenario here? You guessed it. The item you're looking for is the very first one in the list. How many steps did that take? Just one. So its best case performance is Omega of 1. It is physically impossible for it to run faster than that. That's the floor. And there you have it, side by side. Big O, the upper bound, the worst case, our pessimist friend. It won't be slower than this. Big Omega, the lower bound, the best case, the total optimist. It won't be faster than this. You've got the ceiling and the floor. So we have a ceiling and a floor, but what happens when they touch? What if the best case and the worst case are basically the same? Well, that's where our final piece of the puzzle comes in. Big-Theta. This is the Goldilocks zone. We pull out Big-Theta when an algorithm is super predictable. Its best case, its worst case, they're the same. This is what we call a tight bound. It's not too slow, it's not too fast, it's just right. The performance is basically locked in, no matter what you throw at it. And the perfect example of this, just printing every item in an array. I mean, think about it. Does it matter if the array is sorted or backwards? Nope. You have to touch every single one of the n items to print them. The best case is n steps, and the worst case is n steps. So we can say with total confidence that its performance is theta of n. Okay, enough theory. Let's take our new vocabulary out for a spin with a real-world case study, the legendary Quicksort. This is where you'll see why knowing all three, O, Omega, and Theta, is so important. Whoa, look at that range. On a good day, Quicksort is flying at a beautiful Omega of n log n. But on a bad day, oh, it's a disaster. It slows to a crawl at O of n squared. That is a huge difference. So what's the deal? What separates the hero from the villain here? It's one tiny crucial detail, how you choose your pivot. And here it is, the source of all our problems. See that line in the Python code? Pivot equals array at index 0. Danger. Just always grabbing the first element is a terrible idea, because if you feed it an already sorted list, you get the worst possible split every single time. And that's how you end up in that n squared nightmare. And don't go blaming Python. This is a logic problem, not a language problem. Check it out in C++. Different syntax, sure, but look, pivot equals array at index low. It's the exact same dangerous idea. The same trap is waiting for you. And just to really hammer it home, here it is in Java. See? Pivot equals array at index begin. It doesn't matter what language you're speaking. A bad pivot choice is a bad pivot choice, period. It's a fundamental flaw in the algorithm's implementation, not the syntax. So how do we dodge this bullet? Simple. We get smart about the pivot. Instead of just grabbing the first one, what if we pick a random element? Or even better, the median of 3 random ones. Suddenly, the odds of consistently picking a bad pivot drop to basically 0. The partitions stay balanced, and the performance becomes so consistent that we can confidently call it, you guessed it, theta of n log n on average. Now that's a reliable algorithm. Okay, your turn. Let's say you're building something for real, a critical system. What do you care about more? The best case scenario, that Omega promise of speed, or the worst case guarantee, that Big O safety net? Think about it. Do you plan for the best or prepare for the worst? Your answer says a lot about how you build things. So as we wrap things up, I want to leave you with this golden rule I live by. If it's confusing, draw it. If it's important, highlight it. And what we learned today is definitely important. Big O is just the headline. To really get it, you need the whole story. The O, the Omega, and the Theta. That's the full picture. So I'll leave you with this one last thought. The next time you're looking at a piece of code, are you just going to slap a Big O label on it and call it a day? Or are you going to be more precise? Are you going to use the full language we learned today to describe exactly how it behaves? The choice is yours. Thanks so much for hanging out with me.
Hey everyone, I'm Cody, and today we're going to pull back the curtain on a core mystery that every single programmer faces.
Have you ever wondered why that is? Why some code is just blazing fast, while other code feels like you're wading through molasses? Well, the secret isn't some kind of dark magic. It's all about understanding how your code behaves under pressure. So let's break it down.
You see, algorithms aren't one size fits all. They're a lot like people, actually. They have different moods, or to be a bit more technical, different performance cases. We call them the best, the average, and the worst case.
First up is the best case. This is the absolute dream scenario, right? The stars align, everything goes perfectly. Imagine you're looking for a book in a huge library, and bam, it's the very first one you pick up. That's an algorithm in its best case. It's peak efficiency, but let's be real, you can't count on that happening every time.
Next, we've got the average case. Now this is reality. This is the typical day in, day out performance you're going to see with just normal mixed up data. For most of the applications you'll ever build, this is the case that matters most to your users. And finally, the big one, the worst case. This is the ultimate stress test. It's when the data is lined up in the exact way to make your algorithm's job as difficult as possible. Understanding this case is absolutely crucial for building reliable, bulletproof software that doesn't just fall over when things get tough.
To see all this in action, let's take a look at a real champion of efficiency, binary search. The logic here is just beautiful. In a sorted list, you check the middle element, and right away you get to throw out half of the remaining data. This whole divide and conquer strategy is just incredibly fast.
And what's so powerful is that this core idea is totally universal. Here it is in Java. Yeah, the syntax is a bit different, but that core strategy of just narrowing the search space is identical.
And you guessed it, same story again in C++. This is such a crucial point. The language is just the tool. The algorithmic thinking is the real skill.
Okay, now this is where the rubber meets the road. We use something called Big O notation to describe performance. Think of it like a report card for how well an algorithm scales. Now look at binary search. Its worst case is an amazing O log n. It barely gets slower as you add more data. But then you look at bubble sort. Its worst case is O n squared, which gets slow really, really fast. This is exactly why we analyze cases, to avoid total performance disasters.
Okay, so we've got the theory, but how do you decide which case to focus on in the real world? Let's look at how this actually applies to making decisions.
Well, it completely depends on the job. For something critical like air traffic control, you absolutely must guarantee performance even in the worst conditions. I mean, lives are on the line. For your typical web app, you're going to optimize for the average user's experience. And in some rare specialized systems where you know the data structure inside and out, you can even get away with optimizing for the best case.
So, quick question for you. Think about a photo sorting app on your phone. Would you be more concerned with its performance on a typical day, or for that 1 in a million worst case scenario? You got it. You'd optimize for the average case. You want it to feel snappy for everyday use.
All right, let's shift gears. We've seen how to analyze performance. Now let's explore a really powerful and, I gotta say, elegant way to write algorithms, recursion.
Recursion can feel a little mind-bending at first, but this analogy makes it so simple. A recursive function solves a problem by calling itself with a slightly smaller version of that same problem until it gets to the smallest, simplest all that it can solve directly. So, here's the crucial part. Every single recursive function needs two things. First, the base case. This is the smallest all, the condition that tells the function to stop calling itself. Second, you have the recursive case, which is where the function calls itself, getting one step closer to that base case. If you forget a base case, you get an infinite loop, and nobody wants that.
Recursion can lead to some of the most elegant and clean code you'll ever write. It's awesome, but with that power comes a few hidden traps you really need to watch out for. Let's look at the classic example, calculating a factorial. The base case is simple. The factorial of 1 is just 1, easy. The recursive step is n times the factorial of n minus 1. See how the problem gets just a little bit smaller with each call?
And this is what's happening behind the scenes, which is so cool. The computer uses something called a call stack. Each time the function calls itself, it adds a new frame to the stack. Once it finally hits the base case, it solves that, and then it unwinds, passing the result back up the stack one call at a time.
Now let's look at another famous recursive problem, the Fibonacci sequence. I mean, the code looks beautifully simple, but that simplicity is actually hiding a massive performance problem. So if you trace the calls for fib5, you get this big branching tree, and the problem becomes obvious really fast. Look how many times we end up recalculating the same values, like fib of 3 and fib of 2. This redundant work is a classic recursion pitfall that leads to exponential complexity, and it just grinds everything to a halt. So how do we fix it? Well, one advanced technique is called tail recursion. By restructuring the function so the recursive call is the very last thing that happens, some compilers can perform this amazing optimization that prevents the call stack from growing at all, making it as efficient as a simple loop. How cool is that? And that really brings us to the end. Whether you're analyzing worst-case scenarios or designing an elegant recursive solution, it all comes back to this idea. Great code is thoughtful. It anticipates challenges and solves problems with efficiency and grace. So, the real question is, what will you build with these ideas?
Hey everyone, I'm Cody. You know, every single developer has had that moment, that mysterious crash that just leaves you staring at your screen thinking, what just happened? Well, today we're going to solve one of those mysteries. And along the way, we'll master two of the most powerful concepts in all of programming. So check this out. I was working on a program and everything seemed to be going just fine until it wasn't. The whole thing just froze up, then crashed with no useful error message. It's one of those moments, right? Where you just have to scratch your head and go, what on earth just went wrong? I'm willing to bet you've been right there with me. You write code that looks perfect, you run it, and it just gives up on you. Well, today we are going to crack this case wide open together. We're going to debug this thing and add some seriously powerful new tools to our coding toolkit. Okay, so the first set of tools we absolutely need to get our heads around are the two main ways we tell a computer to do something over and over again, iteration and recursion. You can think of them as two different paths to solve the exact same problem. One is like a straight, steady highway, and the other, well, it's more of a winding scenic route. Now, to really see these two paths in action, we're going to use a classic coding challenge that you've probably seen before, the Fibonacci sequence. The idea is super simple. You start with 0 and 1, and every number after that is just the sum of the two before it. It is the perfect test case to see how our two approaches really measure up. First step is iteration, our straight highway. Look at this Python function. We set up our starting values, a and b. Then we just use a simple for loop to calculate the next number, step by step by step. It's direct, it's clear, and it just marches straight ahead until the job is done. And hey, it's the exact same core idea in other languages, like Java. The syntax looks a little different, sure, but that fundamental step-by-step loop, it's exactly the same. This really shows that iteration is a universal bedrock pattern in programming. And let's see it one more time in C++. It's just like following a recipe, right? It's predictable and it's reliable. But you know, as coders, we know there's almost always another way to do things. So what about that winding scenic route? And this This is where things get really fascinating. Instead of a loop, we can use recursion, where a function just calls itself to solve smaller and smaller pieces of the puzzle. The code can look so elegant, right? But just look at these trade-offs. The time complexity, basically how long it takes to run, is O of 2 to the n. That means it gets exponentially slower as our number gets bigger. Whoa, this beautiful, elegant solution has a hidden and very dangerous cost. Okay, time for a quick pop quiz. Let's say you're trying to find a file, but it's buried in a massive system of folders inside of even more folders, a classic tree structure. Based on what we just saw, which approach feels more natural for that kind of problem? The straight road of iteration or the winding path of recursion? Go on, think about it. All right, to truly understand why that recursive solution was so costly and why my program crashed, we need to open up the next part of our coder's toolkit. We need to look at the workspace where our code actually runs, the computer's memory, specifically two areas called the stack and the heap. The absolute easiest way to think about these is with a simple analogy. The stack is like your personal, super organized workbench. Everything has its place, it's lightning fast to grab what you need, and you clean it up the second you're done with the task. The heap, on the other hand, is like a giant shared warehouse. It's a bit messier, yeah, but you can store huge things in there for a long, long time. So let's zoom in on that workbench, the stack. Its golden rule is last in, first out, or LIFO. Just imagine a stack of plates. You put a new plate right on top, and when you need one, you have to take the top one off. You can't just sneak one out from the middle. This is exactly how your program manages function calls. Here's how it works in practice. Every single time a function is called, a new little package called a stack frame gets pushed onto the top of the stack. This frame holds all of that function's local variables. Then, when the function is finished, its frame gets popped right off the top. It's all automatic, and it's incredibly fast. And now for our big warehouse, the heap. When you need to create an object or some data that has to stick around longer than a single function call, you ask the system for some space in the heap. It's perfect for things that need to be shared across your program, or just have a really long lifespan. Managing it, though, is a bit more of a manual process. So here's the side-by-side breakdown. The stack is small, blazing fast, and totally automatic. The heap is huge, flexible, but a bit slower, and you have to be careful about how you manage it. But look closely at that size limit on the stack. That is the critical clue we need to solve our big mystery. Okay, it's time to connect all the dots. We've seen our tools, iteration, and recursion, and we've seen our workspace, the stack and the heap. Now let's see what happens when we pick the wrong tool for the job and completely break our workspace. This right here is the exact recipe for the crash we saw at the very beginning. Remember how every function call adds a plate, a frame, to our stack? Well, with really deep or worse, infinite recursion, we just keep piling on frames, one after another, until we completely run out of that small fixed amount of stack memory. And that, my friends, is a stack overflow. And this is it. The culprit. The simplest, and yet most destructive piece of code you can write. It's a function that does absolutely nothing but call itself over and over. Each call adds a new plate to the stack, until the whole thing just collapses under its own weight. This is almost certainly what happened to my poor program. Mystery solved. But the stack isn't the only place things can go wrong. Over in our big warehouse, the heap, the big danger is something called a memory leak. This happens when we ask for a chunk of memory, like with malloc and C, but then we lose track of it and forget to ever give it back. That memory is now basically lost forever. It's occupied, but totally unusable. So now that we understand how things can go catastrophically wrong with both the stack and the heap, we can be much, much smarter. It really all comes down to choosing the right tool for the right job, so we can avoid these kinds of disasters in the first place. So when should you reach for iteration? Well, you should use it when speed is absolutely critical, when you're dealing with a huge amount of data, or when the logic is just a simple step-by-step process. It's your safe, reliable, high-performance option that will never, ever overflow the stack. And what about recursion? Well, it absolutely shines when a problem is naturally shaped like a tree, like that file system we talked about. When the recursive code is dramatically cleaner and easier to understand, it can be a fantastic choice. But, and this is a big but, only if you can be sure the recursion won't go too deep and risk blowing up the stack. And as you go out and tackle all these complex problems, I want you to remember this golden rule. If you're ever struggling to picture how the stack is working or how a recursive function is unfolding, just grab a piece of paper and draw it out. I promise you, it's the best debugging tool you'll ever have. All right, you are now officially equipped with a much deeper understanding of how your code really works under the hood. So my question to you is this. Think about your own projects. What's the first piece of messy code you're going to go clean up with this new knowledge? Thanks for joining me today, and happy coding.
Hey everyone, I'm Cody, and welcome. Today, we're going on a bit of a mission. We're going to be hunting down the silent killers that are hiding in your code, the ones that turn your most brilliant algorithms into, well, frustrating failures. So grab your thinking caps, because we're diving in. You know the feeling, right? You spend hours, maybe even days, crafting this beautiful, logically perfect algorithm. You hit submit, you're feeling good, and then, bam, time limit exceeded. It is the worst feeling, especially when you know your logic is solid. So what's the ghost in the machine that's slowing you down? Let's find out. All right, it's time to put on our detective hats. In this little investigation, we are going to unmask and neutralize two of the most common, most notorious silent killers of code performance. Think of this as a forensic analysis of your algorithms. Let's get to it.
So our first suspect, this one's a real master of disguise. It's lurking where you almost never think to look. It's not your algorithm. Nope. It's the way your code is talking to the outside world. It's the I/O bottleneck.
Okay, just look at the evidence here. It is absolutely staggering. To read 1 million integers in Python, the standard input function can take a mind-numbing 100 seconds. 100! Your genius O of n algorithm is dead in the water before it even starts running. Now, sys.stand.readline helps, for sure, but sys.standin.read, that's the real game changer. It's literally 100 times faster. So what's the big secret here? Well, think of it like this. The input function is like sending 1,000 tiny messengers, one for each piece of data, and each one has its own overhead. Sys.stand.readline is a bit smarter. It sends one messenger per line. But the true champion, sys.stand.read, that's like sending a giant freight train. It grabs a huge chunk of data all in one go and just crushes that overhead.
And hey, this isn't just a Python thing, not at all. In C++, the default sin is actually held back because it's trying to stay in sync with old C-style I/O. But you add this one little magic line of code and boom, you unleash its true speed. Same idea in Java. Your go-to is the buffered reader for the exact same reason. It reads data in big, efficient chunks.
So how do we actually defeat this villain? Well, the answer is a simple but powerful technique called buffering. It is the secret weapon behind every single fast I/O method out there.
Here's the key idea. Imagine you need to fill a swimming pool. You could use a tiny cup, right? It'll take you forever. Or you could use a fire hose. Buffering is your fire hose. It just blasts a huge block of data into memory all at once, so your program can actually get to work instead of just sitting around waiting.
And this right here says it all. On the left, you've got the tiny cup method with all these little inefficient requests. On the right, you have the fire hose with one massive, super efficient read. We just grab a big 4 kilobyte chunk, process it, and only go back for more when we absolutely have to. It's a total performance revolution. Okay, to make this super practical for you, here are 4 essential patterns you should get down. These templates cover the most common situations you're going to face, from reading one number to handling complex inputs with multiple test cases, and yeah, even writing your output efficiently. Get these patterns in your toolkit, and you'll never get caught by slow I/O again. All right, we've caught our first culprit, but our investigation is not over. There's a second silent killer, and this one is way more insidious. This one preys on your lack of preparation, on the clues you ignore that are sitting right there in the problem statement. This right here, this is a complete game changer in how you should think. That little line that says n is less than or equal to 100,000 isn't just a rule. It's a secret message from the person who wrote the problem. It's a giant flashing neon sign that is screaming the exact type of algorithm you need to use. And it breaks down into this simple 3-step decoding process. First, just find the largest possible input size. Let's say n can be up to 100,000. Second, you got to remember this rule of thumb. A typical server can handle about 100 million operations per second. Third, do the math. An O of n squared algorithm here would be 10 billion operations. That is a guaranteed time limit exceeded. You have absolutely no choice but to find an O of n log n or an O of n solution. And behold, the Rosetta Stone of competitive programming. Seriously, this is your ultimate cheat sheet. If you see a tiny n of like 20, sure, go ahead. You can unleash an exponential beast of an algorithm. But as n skyrockets, your options get real slim, real fast. If n is a million, you better be hunting for a linear time solution. This table is your oracle. It guides you to the right algorithm before you even type a single line of code. Okay, theory is cool and all, but let's actually put this into practice. I'm going to give you 2 scenarios. Your job is to look at the constraints and pick the right tool for the job. Ready? Okay, scenario 1. You've got an array of up to 100,000 integers. Your mission, find 2 numbers in there that add up to a specific target. The clock is ticking. What's your move? So if your first thought was brute force, that's a one-way ticket to time limit exceeded. Now sorting the array and then using 2 pointers, that's a much smarter O(n) log n play. But the gold medal, that goes to the hash set solution, which is just an elegant O(n) single pass. Both of those last 2 will get you across the finish line. All right, scenario 2, let's switch it up. The input size n is just a measly 100 this time, but you have to find the shortest path between all pairs of nodes in a graph. What's your weapon of choice? See, within this small, an O(n) cubed algorithm isn't just okay, it's a perfect fit. 100 cubed is only a million operations. That's nothing. The classic Floyd-Warshall algorithm is practically begging for you to use it here. Running Dijkstra from every single node is also a valid move, though maybe a little less elegant. The constraint basically handed you a get-out-of-jail-free card for a simpler cubic time solution.
And one final super critical piece of intel. Time isn't your only enemy out there. Memory constraints can be just as deadly. A big 2D array that's a total walk in the park for C++, taking up maybe 4 megabytes, could be a memory hogging nightmare in Python at almost 28 megs. You always got to do a quick mental check on your memory usage. And there you have it. We've unmasked our 2 silent assassins. By mastering fast I/O and learning the art of decoding constraints, you have just unlocked 2 seriously formidable coding superpowers. So, let's recap your key takeaways. First, always crush slow I/O with buffered methods. Second, treat constraints as your strategic guide, not just some dumb rules. And finally, the golden rule, plan before you code. Seriously, a few minutes of strategic thinking will save you an eternity of debugging. You are now a certified silent code killer hunter. You're ready to write faster, smarter, and way more successful code. The next time you face a challenge, you're going to see those hidden traps before they ever see you. So, I'll leave you with this. What's the first thing you're going to change in your own coding process? Have you ever stared at a coding problem, found a solution that, works, but you just have that little voice in your head saying, this could be better, right? Faster, a little more elegant? Well, if that sounds familiar, you are in exactly the right place. Today, we're going to crack the code on how to write not just code that works, but code that's absolutely brilliant. Hey there, I'm Cody, and it's my mission to help you level up your algorithmic thinking. We're going to go way beyond just getting the right answer. We're going to start building solutions that are genuinely smart and super efficient. So, let's get into it. And that really brings us to the most important question, doesn't it? It's not just about, hey, can you solve this problem? It's all about, can you solve it efficiently? That one little word is what makes all the difference between a good programmer and a truly great one.
All right, so to really dig into this idea, we're going to take on a challenge. Now, this one looks super easy at first glance, but there's a catch.
So here it is, our mission for today. Take a big list of numbers and find the 2 that are closest to each other. Simple enough, right? I bet you could whip up a solution in just a few minutes. But what if that list doesn't have 10 numbers, but 100,000? Yeah, that's when things get really, really interesting. Now, the very first idea that probably pops into your head is what we call the brute force approach. It's the most direct, the most obvious way to solve it. But let me tell you, it's a trap, and it can lead to some disastrous results. The logic is so simple, it's tempting. You just, pick the first number, compare it to every single other number in the list. Then you pick the second number, and you do it all over again, and again, and again. You just keep track of the smallest difference you've seen so far. It will, eventually, give you the right answer. But at what cost? That cost has a name. It's called time complexity. And for this brute force method, it's O of n squared, or what we call big O of n squared.
Now what that really means is this notation tells us how our program's runtime is going to grow as our input, n, gets bigger. And let me tell you, with n squared, it doesn't just grow, it absolutely explodes.
And here's what that explosion looks like. For 100 numbers, it's instant. 1,000, it's okay, you might notice a little lag. But for 100,000 numbers, our poor little program has to do 10 billion operations. That's not just slow, folks. That is a full-blown disaster. Your program is going to time out, it's going to crash. Welcome to the brute force trap.
So, how do we get out of this mess? Well, the secret, the real pro move, is to stop and think before you even type a single character. We've got to look at the rules of the game, the problem's constraints, to find a smarter path forward.
And here it is, the one piece of information that changes everything. N, the number of items in our list, can be as big as 100,000. The second we see that, we know, without a doubt, our O of n squared solution is dead on arrival. It's a complete non-starter. We are forced to be more clever.
So let's just make sure we're all on the same page. Time complexity isn't about counting the exact milliseconds it takes to run. It's a bigger idea. It's about how the runtime scales. As you add more data, does it get a little slower or a lot slower? That's what we need to know.
And this slide right here, this is the aha moment. On the left, you've got our O(n) squared brute force, which just blows up. But on the right, that's our goal. O(n) log n. Look at it. It scales gracefully. It handles huge inputs like a champ. That is the efficiency we're aiming for.
So, the million-dollar question. How do we get to that beautiful O of n log n performance? Well, it's with a wonderfully elegant two-step trick. First, you sort the array, and then you make one single pass through it.
Just think about it for a second. If you sort all the numbers from smallest to largest, where are the two closest numbers going to be? They have to be right next to each other. It's impossible for them to be anywhere else. That single insight is the entire key. Sorting does the heavy lifting for us.
And here's the best part. You don't have to spend all day writing some complicated sorting algorithm. Nope, modern languages have amazing tools baked right in. In C++, it's literally one line. std sort. Done. The whole sorting step is handled.
And it's the exact same story in Java. You just call arrays.sort, give it your array, and boom, it's sorted efficiently for you.
Python makes it even cleaner, if you can believe it. Just call the sort method directly on your list. See? This super important first step is made incredibly simple for us no matter which language you're using. All right, now for the easy part, step 2. Our array is all nice and sorted, so all we have to do is loop through it just one time, comparing each number to the one that came just before it. We check the difference, and we just keep track of the smallest one we've seen. It's clean, it's simple, and it is unbelievably fast.
So let's check the final score. That sorting step we did, that takes O of n log n time. Our super fast single pass, that's just O of n. When you put them together, the slower part, the sort, is what defines our total complexity. So the grand total is O of n log n. We did it. We hit our target. That's a huge one.
Okay, solving this one problem is awesome, but the real prize here is building the skills so you can solve any problem like this. So let's lay out a quick roadmap to help you get there. Here's a totally doable 4-week plan. Week 1, you just focus on getting comfortable with complexity. Week 2, you dive into recursion. Week 3, you get a handle on how memory works. And then in week 4, you bring it all together by focusing on constraints, which, hey, is the exact skill that cracked our problem today.
And that whole roadmap is really built on these 8 core ideas. These are the foundations of data structures and algorithms, or DSA. From understanding time complexity to knowing how to read problem constraints, mastering these is what separates the pros from the amateurs.
You know, if there's just one single thing you take away today, please let it be this. Our goal is not just to find a solution that works. The best, most beautiful algorithms are the ones that perform like a dream, no matter how much data you throw at them. They don't just work, they scale. So I'm going to leave you with a question. Think about some code you've written or a project you're working on right now. Now that you've got this new way of thinking, what's the first piece of inefficient code you're going to go back and fix?